we go. Where'd we leave off is the question. Oh, so I did want to show you this. And I had a question this morning from one of the students and something I didn't really emphasize and I need to talk about. And how come you're not seeing that? Once again, I got to reduce this. So one thing you'll notice if you're extremely observant is that the lines get closer and closer together as you get further from the nucleus. Remember, as n increases, you're getting further and further from the nucleus. Let's check out what those two chats are. They're not just good mornings and hey, what's up? Okay. All right. So you'll notice the lines get closer and closer together. That's not like just to squeeze it into the picture. That actually has meaning. And what it means is that the energy difference between, that is your first quantum number, by the way. And if you're reading, you know that's your first quantum number. The energy difference between the levels becomes closer and closer and closer together, and less and less and less for a transition. So if I was to ask a question similar to what you had on the quiz, where you had different transitions, and I forget exactly the way the one the quiz was, and obviously they're different for everybody typically. But if I ask something like, which has a greater energy of emission? 2 to 1, 3 to 2, 2 to 6, or 3 to 85? What would your answer be? Emissions, that's got to go down. Very good. And the biggest gap is going to be the 2 to 1, right? I would never ask you this, which is a greater energy of emission, 2 going to 1 or 35 going to 25. It's probably 2 going to 1, but I don't know. I do have to do the math, because there you've got 10 energy level jumps, right? Or even 2 going to 1 or 6 going to 2. I don't know. I'd have to do the math. But the way the quiz one was worded, it was such that you could just look at it without doing the math and deduce what the correct answer was. So your two things you're looking for is the gap between the numbers, but also whether it's emission or absorption. If it's negative, that means it's emission going from high to low, electrons coming back down or relaxing. If it's positive, then that means it's absorbing and going up. So sometimes there'll be questions like the first one I asked you, that some will be going up and some will be going down, and the key is to recognize the emission. Does that make sense? Question, Jeff. What's your name? Tobias?
There's no difference between 2 to 1 and then say like 4 to 3.
Yeah, there is.
So there is a difference.
Yeah, just look at the lines right there. You can that one you can see right there. Look at the gap between 2 and 1 and between 4 and 3, or 4 and 2. That is the difference in energy. Yes, so that's kind of the point I'm making. For any single one level transition, 2 to 1 is always going to be the biggest, right? The next biggest will be 3 and 2. The next biggest will be 4 and 3. They're getting closer and closer together. Does that make sense? Go ahead.
Another question that was on the quiz, it was like given the same setup as the emission, but it was asking the largest wavelength. Would that then be?
Okay, so yeah.
You would just look at like what's the less emission.
Right. So energy is directly proportional to the frequency. So the largest energy is the largest frequency. Okay. Highest frequency, I guess you should say. Which is going to be the smallest wavelength. Right? So you just got to switch it for wavelength, depending on how the question was worded.
Right.
That make sense?
Yeah. So
okay.
Like 9 to, or like say 6 to 5 would have a larger wavelength than 2 to 1. Right.
Right. Yes. Lower energy, larger wavelength. Anything else with this? Okay, let's figure out where we left off. Anybody remember? Oh, is that where we left off, right? Okay. You see both of them yet? All right. Electrons as waves is kind of where we were going. I showed you, this. Talked about the electron having waves. So now here we are. This is the part of the revolution of quantum theory. I'm not going to spend a lot of time on this. This is very mathematically based. I was talking to someone the other day in my office and just saying that, you know, when I took physical chemistry, you literally have to learn like a whole nother language of math. Okay, you have to learn Hamiltonian math and like different types of linear algebra to do it and understand it and really get an appreciation for it. So if you're a chemistry major, you'll take physical chemistry. Especially if you're an ACS major, you'll take the real physical chemistry, like I took. If you're not an ACS major, you take the lower level ones, and if you're a biochem major, you only take one semester of physical chemistry. But let's just say that one of the keys here is that this wave is kind of like around that Bohr orbital, okay? And the only way the waves work is if n is a whole number. Okay, you can see the one at the bottom there. That's not going to work. That's not a wave that works. That interferes with itself, right? You take a little physics, you get a feel for that. So that's one of the keys to this quantized idea is it's the math. This works, and it is the waves have to be whole number multiples, okay? And they're basically oscillations. You can't no longer think about the electron as moving around the nucleus like a planet moves around the sun. It's not the way it works, okay? It's a vibration of energy, if you will. And what we'll realize, it ultimately becomes a mathematical statistical calculation of where the electron is, as opposed to it being somewhere definitively, okay? It's really all I'm going to say about this. You can read a little bit in your book. It doesn't have that much on it, but the key is that the electron behaves, has wave characteristics. So when you hear this particle wave duality, this is what we're talking about, okay? Einstein said light is composed of photons, particles, packets of energy, right? And now Broly's saying they have wave characteristics. That's that duality. This is unique at this time. There was waves and there was particles. There was nothing that behaved like both. So this is what's new about quantum theory. Then we get into the Heisenberg uncertainty principle. And I've skipped, let's see. No, I still have some of that here, okay. Heisenberg uncertainty principle states that one cannot simultaneously know the exact position and exact momentum of an electron. Now, what you have to appreciate here is this is not some sort of limitation to human technology that eventually we'll figure it out. No, that means you don't really understand it if that's what you're thinking. This is an actual aspect of nature, a fundamental intrinsic aspect of nature. What we mean by this is that anytime you observe something in nature, there has to be an interaction of electromagnetic radiation with matter. That's how you're seeing me stand up here, right? That's how you're seeing your paper. The electromagnetic radiation, light is reflecting off there. If I turn off the light, you can't see anything, right? You shine a flashlight, you turn on your phone flashlight, you can see something. So you always have to have interaction of electromagnetic radiation with matter, and then it reflects to your eye and you see that. Well, the reason Heisenberg's uncertainty principle holds is because electrons are incredibly small and have a very small mass. So as soon as the electromagnetic radiation interacts with them, it affects them. It changes their speed, or I should say their velocity, because velocity has magnitude and direction. Speed is just direction. I mean, speed is just a magnitude, no direction, if you take physics. So the very interaction of the light with the electron changes it. So I'm going to violate what, Feynman says, not to give analogies, because there's no real analogies that you can rely on. But the best analogy I've ever seen is kind of, I grew up I'm a big photography fan, and I grew up, using film and developing my own film and taking film photography. And if you've ever, and you can do it with digital too, of course, taking a time-lapse photograph of a car going by, okay? You can start it, right? Say it's at night, you get the streaks of light, and then you stop it, you know how long your shutter's open, you can measure the distance the car went, and you can calculate its velocity. which tells you it's momentum. Momentum is just mass times velocity, right? So you can replace momentum with velocity, it doesn't matter. But I don't know where the car is at any moment in time. It's just a blur of light. You can say, well, yeah, maybe it's right about here now, but you don't know exactly, right? It's just a blur of light. Or you can take a snapshot. And when you take a snapshot, you know exactly where the car is at that moment, but you have no idea how fast it's going. That's the best analogy I've ever heard of. It's not my analogy, someone else that used that. And that's kind of the way it is. And the key to it is the fact that electrons are so small that they're affected by the electromagnetic radiation. Now, if I roll a bowl across the floor here and we shine a flashlight on it, that's not going to affect its velocity, right? So you can calculate it you can calculate position and velocity for a ball. You just can't do it for subatomic particles. They're too small. And it's, once again, it's not like we're eventually going to be able to figure this out. No, because any wavelength we need to detect the electron is going to be too energetic. And it's going to cause that electron to change. Does that make sense? Questions? And I did this the other day, just showing you the difference. Because the electron has a smaller wavelength, you get better resolution. That's physics and why that works, but just know that the smaller the wavelength, the better the resolution is, the better image you get. And electrons have much smaller wavelengths than visible light. So quantum mechanics is the part of quantum theory that has all that advanced math I was telling you about. Mathematical description of the wave-like behavior of electrons and other particles was needed. So Erwin Schrödinger, another Nobel Prize winner, along with Heisenberg and Planck and Einstein and de Broglie, I believe. I think Pauli wins the Nobel Prize too. Anyway, he developed quantum mechanics, and his wave equations describe electron waves. The solutions to the Schrödinger wave equations are wave functions, that's just a symbol we use, psi, which describe how the electron matter wave varies with location inside the atom. So he developed all this math, and the solutions to this math tell you basically statistical probabilities of where the electron is. Okay. Max Born, I think he might have won the Nobel Prize too, proposed the square of the wave function, defining what is these orbitals now. This is not the orbit like the Bohr orbit. Okay. Bohr's model was incomplete. That's okay. That's why science works, right? We built on ideas as we moved along. We realized it's not an orbit, it's an orbital. Three-dimensional region of probability of where the electron resides around the nucleus. So this is the spraying. If you spray something like this, is kind of the idea. And you can define the region however you want. You can define the region where I find the electron 90% of the time, which is common, 50% of the time, 10% of the time, do whatever you want. Obviously, it gets smaller, the smaller your probability. Okay. So the quantum numbers, which Megan has got a question about, are the solutions to these equations. So they're parameters in the equations. You really can't appreciate them until you've looked at some of the math. So if you take physical chemistry, or even depending on what physics, if you're a physics major, anybody a physics major? Oh, how disappointing. Physics majors. If you're a physics major, you can go into the stuff even more than chemistry majors do. All right, so each orbital is defined by a unique combination. It's kind of like an address. You know how your address gets more specific and specific? Like it starts out, hey, I live in Tennessee. Then it's like, okay, the zip code maybe gives the region, right? Then you've got your street, right? And your house. And it kind of gets more and more specific. That's kind of what the quantum numbers do. The first one tells you the general region. The next one zooms in a little bit closer. That's kind of what it is. And ultimately, the idea is, to assign electrons in atoms locations within orbitals. And it sounds esoteric and everything, but what you don't realize is all this stuff goes to developing new materials and technologies. It's all used. Quantum theory isn't some sort of, abstract science that no one uses. It's exact opposite of that. It's the essence of so much of the technology that advances our computers, our materials, understanding all sorts of like bonding and stuff like that allows us to develop drugs and new materials and new cells for, like photocells and things like that, for renewable energy, all this type of stuff. So it isn't something that's obscure and abstract. So we have now is the principal quantum numbers, the one because that was in Bohr's equation. That's the end that you see in Bohr's equation. Okay, it's the same one up there. There's the angular momentum quantum number. I think it's also called the azimuthal. I think that's one of the ways it was referred to. Maybe they don't use that much anymore. That's L. And then the magnetic quantum number is ML. Okay. And I think it's on the next slide. I'll just go to the next slide, so it's explaining it here. So we're going to be coming back to this. So hang on for a second. Let's do this right here. The principal quantum number N. It's a positive integer describing the relative size and energy of an atomic orbital or group of orbitals in an atom. Okay. It's the first quantum number. It's the principal one, and it gives you a general location for an orbital. And it tells you the size, if you will. The angular momentum quantum number, the next one, it has integer values from 0 to up to n-1. All of those values, not just n-1. Remember, these are solutions to equations, and you'll see where this goes in a bit. Orbitals, so N's kind of telling you which energy level it's in, and L is telling you which orbital in that energy level, because there'll be multiple orbitals within that energy level. Orbitals with the same value of N and L are in the same subshell and have the same energy. I guess I should read it. I should correct myself. L is going to tell you the subshell. We need ML to tell us, which orbital is really. L's values up to n-1. So those letters, these come from old spectroscopy stuff. Don't ask me, what they are. I can't remember. It comes from old spectroscopy stuff. But basically, L equals 0 is S, 1 is P, 2 is D, 3 is F. That's all you'll ever have to do. But then it keeps going. Okay. The magnetic quantum number M with a subscript of a cursive L defines the orientation of orbital in space. An integer that may have any value from negative L to positive L. Okay, so for each L, there's ML values, where L is the angular momentum quantum number. If L is equal to 1, then ML will have values of -1, 0, and 1. So it's the orientation of an orbital, but it's the specific orbital within that subshell. Okay, just hang on for a second. Let's hold off on the spin quantum number. We don't need that just yet. Let's go back here now. N equals 1. The only allowed value of L is 0 because L is up to n-1, right? And 0, you have to memorize, is S. That's what we see here. 0 is S. There's only one allowed value of ML, 0, because remember, ML is negative L up to 0 up to positive L. Okay, so you can only have one value, 0, which means we only have one subshell. Whoops. One shell and one subshell in this N1 energy level. But if you go to N equals 2, you'll notice I have two possible values of L, 0 and 1, because it's everything up to n-1, right? And then for each of those, you have, there's this here. That's exactly the same as this right here. It repeats itself at the next energy level, but now you have p orbitals available and you have 3 values. So if effectively Subshell. What are the 3p orbitals? Yeah, this is a little confusing where it's listed as subshell. It's the p subshell with 3 orbitals in it. This figure doesn't have it actually, the number of orbitals. Oh, wow. Okay, so I'll have to add that. The old book had it a little bit differently. This is the 3p orbitals. Okay? There's only ever going to be one s orbital, okay? Those are the 3p orbitals. It's really the p subshell, and this really should be orbitals with 3 orbitals. So the subshell is right here. There's the subshell designation. I think that's a typo. That should be orbitals there. Okay, so there's your subshell right there, and that's the number of orbitals. So the second energy level has 4 orbitals, 3p and 1s. Keep going, and you follow the same rules. 0, 1, 2, SPD, and there you go. Now you have 5 possibilities. 5 orbitals. You have 9 orbitals within that shell. Oh, there it is. Sometimes I get tunnel vision. So it says orbitals right there. Okay, that makes sense. So it's not a mistake. It says right here, number of orbitals. Right above where I was pointing. Right there, number of orbitals. That's okay. I thought it was saying that was number of subshells and numbers of shells. It's number of orbitals within the shell and in the subshells. That's fine. Your figures, your table's fine. Megan.
So this isn't like my actual question.
Okay. You're holding on to that one.
Yes, I am. So like, is this just a concept or is this like an actual, like a subshell would be inside a shell?
Right. So there's no analogy I can give you. Some people say sometimes like the peeling of an onion, but that's not accurate because what you'll see is some of the outer subshells penetrate into the inner some of the outer energy levels penetrate into the other ones. So it's not like an onion. Oh, it's not a concept. It is a mathematical calculation. So what you're witnessing is basically the solutions to the equations that predict all the energies of the electrons in a multi-electron atom. That's what we're doing. We're getting away from what Bohr did. Bohr was only dealing with hydrogen or any of one of the electron atoms. Bohr's model was capable of describing lithium 2+, helium +1, hydrogen, right? Only one electron atoms, that's it. This is going to allow us to deal with multi-electron atoms. But what these are energy levels that are calculated where the electron resides. So it's not a concept, it's a reality of where electrons are, but it's a statistical probability. Okay, so there's no definitive, just like I could say, statistically, you're more likely to get COVID if you're not vaccinated, you're not masked up. Doesn't mean you're going to get COVID. Doesn't mean you're not, whatever. Doesn't mean if you're vaccinated and masked, you won't get it. It's a statistical calculation. And these are energy regions around the nucleus where the electrons reside.
But we can't see it, so it's just like a probability.
You can't visualize it. No, you can measure it. Okay, you can measure energy levels, and we can do this by, ionizing atoms and measuring the energy necessary to move the electron in different sequential steps to get experimental empirical data that supports the theoretical model. Yeah. Yeah, so don't think about it. So if an electron has an N of 3, the electron could be anywhere in those options. Yes, Mary, that's right. That's a good question. Where the electron resides will depend on the electron and what the conditions are of the particular atom. If it's a ground state electron, hydrogen is always going to be in the S. But all those energy levels for hydrogen still exist. In fact, we measure out in space, we can determine, like, out there, atoms are very rare, right? You have a vacuum. And as a result, it's incredibly low density, right? Here's an atom out there in space. The next atom, who knows where it is? So we've actually measured spectroscopically electrons in really high energy levels, way beyond this. Usually down here, you're not going to see that, because if an electron's that far from the nucleus, something else is grabbing it, because right next to it is a bunch of other gas molecules and atoms that are electron hungry. Okay, so they are there, they're energy calculations, but it's kind of like saying, like, I don't know, I can't come up with an analogy. Trying to do something with sound, but it doesn't really work. So well, I guess you can do it with any sort of energy level. I mean, you can calculate different energy levels for things other than electrons and stuff like that, the energy of a fire, stuff like that. They're possibilities. That's what they are. They're possibilities.
So electron configuration, is this kind of like the math that goes,
Yes.
that explains it?
Right. So the math, that's where we're going next with the electron configuration. The math is going to take us there. So that's where the 1s2, 2s2, 2p6 is all going from, is where those electrons reside. Well, yes, but what quantum theory did was explain why the periodic table is arranged the way it is. That's the genius of it. Now we understand all the electron configurations, and what we're going to do ultimately is, yeah, you guys aren't going to do the math to figure this out. You're ultimately going to follow the periodic table. But that's the beauty of this. It explains the arrangement of the periodic table, because remember, even though they're arranged in order of increasing atomic number, their characteristics are dependent on their electron configurations. Chemistry is all the interchange of electrons. We don't even, the nucleus is not involved in chemical reactions, right? I'm talking about bonding and combustion reactions and redox reactions. That's all electrons. So that's all dependent on the electron configuration. And when we say that elements that are under each other have similar properties, they have similar properties because of their electron configurations. Are you good? You want to ask that other question?
So for quantum numbers in the book, they have like rules and restrictions too.
Right, right.
I just had a question about how each subshell has a like 2L plus 1 orbital.
Yes. So 2L plus 1 gives you 3. That's all it is. So that's a good question. So it's just the math, just the way it works out. Also, the number of the number n squared is the total number of orbitals in the shell. Right? 3 squared is 9. 4 squared is 16. So n squared is the total number of. So good question. Yeah, that's just the way the math works out. Okay? Is that you can now say that 2L plus 1 is going to be the number of orbitals in the subshell, and n squared is going to be the number of orbitals within the shell. Is it me or anybody else warming? Of course, I'm walking around talking like a maniac. You guys are just sitting there. So that brings us to the spin quantum number, because it turns out when they went back and looked with better spectroscopes, they started to see that some of those single lines that they thought were in hydrogen and these other elements were actually dual bands of light, doublets. If you look really close, you have to have a really good spectroscope. You're not going to see that in lab. Which meant they were getting basically 2 electrons with the same energy, and that violated what they were talking about here, because the idea is that this is a specific address for every electron. And now they're saying, well, wait a second, we're seeing 2 electrons, the same energy. How's that possible? Well, Pauli comes along. Oh, no, not Pauli. Who does the? Is it? Why am I drawing a blank? It is Pauli, isn't it? He's, yeah. He builds on what a couple other scientists do. But the idea is that now we have to add another quantum number because it's like we have 2 houses at the same address. 20 Main Street. Well, it must be a duplex, right? So one's going to be plus a half, and one's going to be minus a half. Now we can distinguish. And what that's also doing, it's a little bit more complicated than just saying, oh, we got 2 electrons there, let's give them 2 different numbers. They're actually different spins. Okay, they have complementary spins. And they're linked by their spins. And that is, one is going to spin the opposite of the other always. And if one changes, the other one changes instantaneously. So that's the 4th quantum number. Okay. Now you have a specific address for every single electron in every multi-electron atom. Questions? So let's see what this one says. It's from your book. What are the names of all the subshells in N equals 4 shell? We kind of just saw this in the chart, right? So for N equals 4, what are my possible values of L? Andrew? Well, more than just 3, right? What are all the possible values? Thank you. 3, 2, 1, and 0, right? Okay, you can do this, right? 3, 2, 1, and 0. That's where we're at. So effectively, you've got your S, P, D, and F. Those are, for the 4th energy level, the case. Okay, so now for each of these, there are ML values, right? So what are the ML values for 0? We'll start on the right. What are the possible ML values for 0? Just 0, right? How about for 1? Right, so we got -1, whoops, -1, 0, and 1. And then we can keep going, right? -2, -1, 0, 1, and 2. -3, -2, -1, 0, 1, 2, 3. Okay. So effectively, we have and you can just name all these. We have a 4S, right? You have the 4P1, 4P2, 4P3. They usually use X, Y, and Z for that. You got the 5D orbitals within the 4th energy level. And you got the 7F orbitals. How many orbitals are in all the subshells of the N equals 4 shell? We just did this. It's just 2L plus 1. Okay, there's going to be 7. So let me point this out. It doesn't matter if it's 3D or 4D. How many orbitals are there in that subshell? 5. Houston's right. It's always 5. If it's 3D, 4D, 5D, why? Well, because these are the D is always 2. So the ML values are always going to be -2, -1, 0, 1, and 2. That is your 5 orbitals, right? It doesn't matter if it's 3D, 4D, 5D. That doesn't change. What changes with the increasing N is the higher options. you can't have F when n equals 3. It's impossible mathematically, right? If n equals 3, you're not going to have an L of 3, right? And if you don't have an L of 3, you can't have an F subshell. So the math dictates which orbitals are allowed in each energy level. This was straight from the book, so this is 3.8, which is right here. Questions? So we can look at allowed quantum numbers. Which of the following combinations of quantum numbers are allowed? And if you raise your hand to answer it, I'm going to ask you, why isn't it allowed? You tell me why. Either correct it or tell me what's wrong with it. In some cases, there might be more than one way to look at it. The first one, anyone want to try, is that allowed? No. Houston says no. You're shaking your head no. What's your first name again? Sonia? Why are you saying no? N is 1, L cannot be 1. Why? L can only be up to n minus 1. So that by it. NL's fine. The problem is this right here. This cannot be 1. So this is not a valid set of quantum numbers. Does that make sense? How about the second one? Yes, as in allowed. You agree with Houston? Is that allowed? So L is equal to 0 when n equals 3. That's allowed. Good. Stand your ground. It is allowed. I'm just challenging you. Yes. Yes, because all the values of, and what he said was, what's your name? Tommy? Tommy said L cannot be equal to n ever. No, because the value, and I didn't say that. I should have said that. But the values of L are up to n minus 1. So it can never equal n. So very good. Another way to think about it that maybe clicks better with you. Hey, oh yeah, L can never equal n. So I asked you, I challenged you, and that's correct. That is right. A lot of people will say, well, no, L has to be 2 when n equals 1. No, it can be 2, 1, or 0. So some people get tripped up by that. Oh, we said, oh, it has to be n minus 1. No, everything up to n minus 1. So if you were to call that orbital, what is it? What's the name of that orbital? Start with the principal quantum number. It's 3, and L is S, right? So it's a 3s orbital. That's a 3s orbital. You can have P's and D's in n equals 3, but this one is a 3s orbital. How about number 3? Is that allowed? Who said no? Houston again. Anybody other than Houston? She's right. Why? What's wrong with it, Houston? Right. So ML only has values of negative L, 0 to positive L. And if L is 0, the only value of ML allowed is 0. That can only be 0.
You had a question in the chat.
Oh, was a good question. How would you name it if it was N3 L2 M minus 1? So the question is, if we have an N3, oops. N is 3, L is 2, ML minus 1. So this is a third energy level, right? And S is what letter? I mean, S is what letter? L is what letter? D, right? 0 is S, 1 is P, 2 is D. So it's a 3D orbital. You don't designate. Now, what they do is you don't have to do this, but there'll be like 3DX, 3DY. You'll see that in the book. 2PX, 2PY, 2PZ. So you don't have to worry about that. It's just a 3D orbital. The ML, for our cases, is not going to be designated. So at some point, you'll see it in the book where they'll like distinguish between the different. I think it's when they start to show the diagrams, maybe they'll distinguish. There they are. You know, on page 111 in your book, you'll see 2PX, 2PY, 2PZ, and different notations for them. The p orbitals are the ones that are like dumbbells. And this is no different than like holding, if you had a bunch of balloons and you hold them all by the nipples where they're tied, are they all going to point upwards? No, they're going to spread out to release, to minimize the energy and tension between the balloons, right? It's impossible for them all to point up. It's not impossible. It's improbable. It can happen theoretically. No different. The orbitals are going to orient themselves in space to minimize repulsions and things like that. That's what these boundaries are. They're defined by the math. So we said this was a no, right? And the last one, is that loud? It is not allowed, Megan says, because of what? Right. So that's no good right there, because the only ML values will be -1, 0, and 1. You cannot have 2. Questions? Gotta love this stuff, huh? I'm going to go through this a little bit quickly because I don't really hold a lot of responsibility on this in the exam. You might see one multiple choice question from some of this stuff. These are kind of like the statistical calculations, okay? And atomic orbitals have three-dimensional shapes that are graphical representations of that psi-squared function, which is the spraying of that, thing. That's to give you the idea. Okay, the shapes of orbitals impact the energies of the electrons in them. So you always think about these as like energy fields rather than actual like existing entities. So one of the analogies I've heard before, because what you'll start to realize as you see some of this stuff is that let's take a look at these p orbitals. So this is one of the p orbitals. There's 3 p orbitals, right? Always. Doesn't matter if it's 2p, 3p, 4p, 5p. There's always 3 p orbitals. Let's say the electron's right here. We measure it and it's right there. We don't know how fast it's going because we can only locate it. Next time we measure it, it might be over here. But what this is right here, it's a node, which means the electron can never, ever be found there mathematically. And that's, that's the nucleus. At the nucleus. That's when matter ceases to exist. If the electrons, that's what's beautiful about quantum mechanics. Classical physics would have said electron goes around the atom like this. Well, if you take physics, it's going to decay over time. It's going to lose energy and spiral into the nucleus. Bohr's model forbids that because there's no allowed energy states below n equals 1. It can never be below the ground state. So it can't possibly ever exist at the nucleus. So the question becomes, well, if it was here at one point and here at another point, how did it get from here to there if it can never pass through the middle? Well, that's because you're asking the wrong question. This is not a ball that rolls across the floor. The best analogy of that, actually, I came up with this one. I'll take credit. Imagine a body of water, okay? And you have a choppiness of the waves if a boat went by or the ocean, whatever. Imagine instead of water, it's like an energy field, okay? And you see a little rise right there and it disappears. That was the electron. Its momentary existence right there it dissipates back into the energy field, and then it appears over here. Is it the same water? Well, I don't know. Did it move from there to there? No. It's just, think of the entire ocean as an energy field, and these are ripples in the energy field. And those ripples are, if you will, kind of the electron for that moment. Then it dissipates and appears over here. But it happens simultaneously. It has to, because there's no time period in which the electron doesn't exist. So the water analogy doesn't work. That's why none of the analogies work. With water, you'd say, well, that wave's gone, really ceases to exist, and another one forms over here. That's not the case for the electron. It's the same electron. It never ceases to be detectable, yet it somehow went from a region over here to here without ever passing through here. That's the, you're not going to be tested on that, just to give you an appreciation for the fact that this stuff doesn't fit into your little, mold of things. Okay, and that's kind of what's, to me, beautiful about it, is the fact that it's kind of beyond what we can conceive of, and we know it's the case because it's been tested numerous times, and all the data works and all the models work, and we can predict all of this stuff, so the model works.
How could we test that?
How can you test what?
Like an electron being here 1 second, and then it not, and then a different.
Well, we can
one
detect
possibly.
electrons in their, we can detect their locations.
Could we do that?
Yeah, so you can use, well, that's a good question. I don't know if I have the tools to answer that, how it's done. I'd have to get back to you on that one, actually. I don't know. How they do this, these studies. Diffraction patterns like that, those types of experiments won't answer it. If you want to watch something really interesting that'll kind of like blow your mind a little bit, just Google the double slit experiment. It's a famous experiment. I'm not going to spend time going over it. I've done it in the past. You Google it and you watch it, and then you start to realize it's what kind of helped understand how electrons are waves. It's a diffraction pattern that electrons give you. So yeah, it's a good question, Megan. I don't really feel comfortable answering that, so I'll see if I can get you some information. All right. So I don't think I need to say anything else about these. You can look at this in your book. This is what I was talking about before, about the penetration. This gets a little bit beyond the course. This is what I wanted you to say, why it's not an onion. You see, this is n equals 3 here with a 3s orbital. It's not like this is 3s, this is 2s, and that's 1s. This is all 3s. Okay, so you can see it's got a low probability of being in this region right here. And what you're noticing here, distance to the nucleus. What's interesting is the distance, it gets a real, you have a peak probability, but then it drops off because it can never be at the nucleus. And what you have to realize too is the electron density, the density becomes so high because the space becomes so small. And as you try to calculate, that's why this is shooting up like this. Where they have, there's a different diagram too. Here it is. This is what I was looking for. This one here, the density. That's effectively what keeps it from ever residing at the nucleus. The density is so high, and you can't have the electron at the nucleus. It would violate the quantum numbers. So you can read a little bit of this stuff, but don't kill yourself over it. This shows you the p orbitals. This is the d orbital. Most books don't even show you the f orbitals because they get so ridiculously looking. The weird donut shapes, but they're all from computer models of the math and how the math comes out. And we have people in our department like Dr. McDougall and my closest friend, actually, Tibor, Dr. Korostonsky, just passed away. Actually, he died in a pretty bad car accident over the summer. 2 days after being at my house. This is his area. Him and McDougall could probably answer your question and how these are done. McDougall was more computational, and Korostonsky was computational, but he did X-ray diffraction studies and things like that too. So actual laboratory work as opposed to just computation. All right. So as a result of all the math, this becomes the filling order. I think I added it. What happened to my figure? Heck. Somehow I didn't replace it. I added a figure here. Anyway. Yeah, what the heck happened to that set of slides? Has to be in Dropbox. Anyway. So this is the filling order. Some people call it the Afbois principle. It's the order in which they fill. And the only thing I want to point out, and that was why I had this other figure in there, it shows it better. But you'll notice things like 4s fills before 3d. And this is where we're going to get to the periodic table, which was your question about the periodic table. If you follow the periodic table, you'll see that 4s fills before 3d. And we'll get to that in a second. I guess that's not here. The table comes up later, I guess. Well, there. Well, that's one figure there. That's not the one I fit in. All right, let's hang on to it. It's further on in my slides. But this is the filling order. Okay, just hang on to the fact that 4s fills before 3d. It's got a higher principal quantum number, so you would say, okay, 3d would fill first, right? Well, just energetically, it doesn't. Actually, it turns out the 4s has lower energy than 3d, and that's all that matters is what the quantum mechanics shows us mathematically. So as we fill orbitals with electrons, we follow the Aufbau principle, which states that the electrons are placed in the lowest energy orbitals available. Okay, and you won't have to memorize that because you'll just follow the periodic table. So this is something your book talks about now. I'd like to do this a little bit later usually, but I guess with the new edition, I've got this up first. Effective nuclear charge. So there's a lithium zone. Yes, we're doing this before we've really done the electron configurations. Okay, so lithium has how many electrons? 3 total electrons. Its atomic number is 3, so it's 3 electrons. So here's our periodic table. There's lithium with 3 electrons. Okay. So here's the first energy level. So the period corresponds to the energy level. And the only subshells in the first energy level are S, right? We already decided we can't have P, D, anything like that. So we have a 1s orbital. And each orbital can hold 2 electrons because we've got the positive and negative spin. So they can have separate addresses, right? So the first 2 electrons for lithium are going to go into the 1s. Now, little 2 subscript tells you there's 2 electrons in the 1s orbital. That corresponds to kind of, if you will, these 2 electrons. Hydrogen would be 1s1, helium would be 1s2. Lithium has another electron. It's going to be in the second energy level, so it'll be 2s1. Okay? S occurs before P. This is all your S over here. This is your P over here. This is your D here. And this is your F down here. You'll see that in a figure coming up. But I wanted to show that because we've got this effective nuclear charge we're talking about. So I wanted to at least show you the electron configuration of lithium, where it's coming from. It's got 3 electrons. You go back and look at the right here, 1s, 2s. That's what we're filling first. And that's what we got in lithium now. So we got 1s2, 2s1. The outer electron. Well, there is no 2p electron, so why do they have a 2p here? I'm not sure. The outer electron is shielded from the nucleus by the inner electron. They meant to say your 2s electron. Or maybe they're saying theoretically, if you had a p electron, they're not doing lithium. I don't know, but it looks like lithium with 3 protons. So that's not a great slide. I just picked up on this. But the point is, it doesn't matter. Any of the outer electrons are going to be shielded by these 2 here. So what the effective nuclear charge is the pull that the nucleus has on the electrons. That's what Z effective is. Effective nuclear charge. And what we're saying is that the pull on the electrons here, these 2, will be greater than on the electron here. It's further away, plus it's shielded by these 2 other electrons. That's what effective nuclear charge is. That'll come into play when we get to the periodic table and start to explain some of the trends. So we do need to talk about effective nuclear charge. And I'll come back to this. Any question? Yes.
Does the 2s1 have like a lower frequency than the 1s2?
Lower frequency, it's a higher energy electron, so it would have a higher frequency. Yeah, so if it's in a higher energy level, it's got high, if it's in a higher quantum number, that's got higher energy. Higher energy means higher frequency. Okay. Electron configuration for lithium. So it has 2 of these core electrons and 1 what we call valence electron. Valence electrons are electrons in the outermost shell of the atom. So for lithium, it's just 2s, and there's 1 valence electron. And you can often write it with the previous noble gas, so this is a condensed version. When you get up to higher elements, the condensed version is kind of nice. For your exam, I'll probably make sure that you guys know how to write the full electron configurations. There might be a question about condensed too, but I want to make sure you know how to write a full electron configuration. So. Questions? So let's look at the orbital diagram for nitrogen. So these are orbital diagrams where we draw little boxes for each of the orbitals. And if they're of the same energy, we kind of group them together. So you see the 3 p orbitals are grouped together in 1 rectangle with 3 separate boxes because we call these degenerate. Same energy. Okay? And that's because quantum numbers don't distinguish between the 3 2p orbitals. They have the same energy. So when we fill going across, we did lithium, right? The second 2s electron for beryllium, that fills 2s, right? Going back here, beryllium would have a second electron here, right? You can see the way the periodic table is structured. At the end of the S is filled. We're going to move over to the P. Boron would have a 2p1 electron, right? Where's that? Which P does it go into? It absolutely doesn't matter. They're all the same. Most people would draw it in the first one just by convention, right? But these are all the same. So you can put that electron anywhere if there's just 1 here. Okay? This is just, keep in mind, this is our little accounting system. It's not like the electrons are in boxes, right? It's just a way for us to keep track of the electrons. Okay? And then keep moving over. Carbon's going to have a second one. So I have 2 p's, right? Total electrons in carbon is 6. So carbon would be 1s2, 2s2, 2p2, right? That would be carbon. Then you get to nitrogen. Something's wrong. That's right, 2p3. There it is up there. We got the electron configuration, condensed one. We got 3p. You notice I have them spinning all in the same direction. That represents the spin. These two have to be opposite because you have to be able to give an address for each of these electrons. They have to be different. Okay, they have the same energy, they just have opposite spins. Hund's rule says energetically that all electrons will spin in the same direction if they're in degenerate orbitals. And you can measure electron spin. This I know with magnets. So when you get an MRI, okay, it's not electrons, it's protons. But that's what you're doing. You're putting protons in a magnetic field and they all line up. And you get some emissions from that, and that's how you get an image. So you're using quantum ideas for a lot of these instruments and things like this. Same type of thing. Actually, we know the nuclear particles have spins and stuff like that too, not just electrons. Okay, and you can put them in magnetic fields and you can measure their spins and that type of thing. So Hund's rule says, once again, to restate it, then when electrons are in degenerate orbitals, their spins will be in the same direction. That is the lowest state of energy. I'll tell you what I tell all my Gen Chem students all the time. Pretty much everything happens in nature to reach a lower state of energy. So chemical reaction, why this chemical reaction happens and this one doesn't? Because this one doesn't result in a lower state of energy, but this one does. Why are the electrons aligned like that? That's the lowest state of energy, and that can be measured. Questions?
So when you get with the P, is it always going to be 2P?
No, if we're in the third energy level, it'll be 3p. So that first number is the quantum number. Okay, so if we're in the third energy level, if we're looking at, instead of nitrogen, phosphorus, and we're looking to valence electrons of phosphorus, good question. Phosphorus valence electrons would be exactly the same as nitrogen. It's right under the periodic table. The only difference is you would have 2s, 3s, and 3p. But the arrows will look exactly the same for phosphorus because it's right under nitrogen. Hence, that's why phosphorus and nitrogen have formed similar compounds, have similar characteristics, because their electron configurations of their valence electrons are exactly the same. And the core electrons aren't nearly as important. Because when you think about two atoms reacting in a reaction, what's going to hit? The outermost shell. That's where reactions take place. That's where electrons are shared and transferred, in the outermost shell. So effectively, the electron configuration of phosphorus and nitrogen, their valence electron configuration is basically the same. You just got to change the numbers. That's it. So if your orbital diagram looks the same, just the numbers under it are going to be 3s. Now that should have been 3 there. If that's it. That's right. 2s, 3s, and 3p. Does that make sense? So then you have your orbital diagrams for the first 10 elements. And you got the condensed ones too. And remember how we always say the noble gases are unreactive? They used to be called the inert gases. Well, guess why? Because all their electron shells are filled. They're not interested in gaining and losing electrons, and that's what chemical reactions are. There are species coming together looking to swap electrons. That's one way to look at it, right? Why do they do that? Well, I want to get to a lower state of energy. I'm going to grab your electron. I'm more electron hungry than you. I got a greater affinity for it. I'm going to grab it from you. Well, the noble gases have no interest in reacting. They've got a full, complete, right? They're all filled up. And you can guess that, fluorine is pretty darn reactive. Why? Hey, man, if I could find one electron, I'll be in this lower state of energy. So I'm electron hungry, right? And what does lithium want to do? Well, lithium realizes, well, maybe it doesn't realize, it's not like it's conscious. Like lithium gets rid of one electron. See, by having this empty here, it's just like kind of like having this empty here. It's a subshell. It's not quite as energetically unstable, but still, if it can get rid of that one electron, then it's got a full subshell, right? So what does lithium do? Well, obviously, lithium does this. Just like sodium right underneath it, right? That's why they get rid of this one electron. This is why we do the atoms focused or the atoms first approach. So now when we go to chemical reactions, you understand why certain compounds form and things like that. Is that a new chat or is that the old one? Yeah, that's the same one. Oh, so once you fill the boxes, spin starts in the opposite direction. Yes, thank you, Mary. So, yes, so look at oxygen. Once I filled the boxes, now I start putting the spins in the opposite directions. Excellent question. And then you just keep going till you fill. And it really doesn't matter whether the spin is up or down. Just by convention, most people put it in the first box and spin it up. But it doesn't mean anything. The electron could be spinning down. It could be in any of those 3p orbitals, or 2p orbitals in this case. So that's just a way for us to kind of keep track of things. It's not necessarily a definitive location and spin. Other questions? Maybe the figure didn't get lost. This might be it here, and I just put it later in the presentation. Orbital energies for subshells do not follow the diagram for hydrogen atom. Within a given shell, subshells fill in the order of SPD. Some overlap of subshells at higher values of N. Example, 4s less than 3d. This is the point I was making before. If 4s fills before 3d. Now, you don't have to memorize that, right? Because that's what the periodic table tells you. Here we are. There's my S's. There's my P's, my D's, and my F's. Follow the periodic table. 1s1, 1s2, 2s1, 2s2, 2p1, 2, 3, 4, 5, 6. Remember, 3 orbitals. So 6 electrons max for the P. Doesn't matter if it's 2p, 3p, 4p. S's max is always 2 electrons, right? 3s1, 3s2, 3p1, 2, 3, 4, 5, 6. 4s fills before 3d. There it is. It's right in front of you on the periodic table. Why? Because this is where the S's fill. And S is lower energy than the D is here. 4s1, 2, 3d. Wait, why are you doing 3d? What happened to 4d? We're in the 4th energy level. No, the first D allowed is 3d, right? You know that from the quantum numbers because N has to be 3 for your first D to appear. And then it fills. And you'll see when we form ions, it'll be a little tricky because the ions will actually leave there first. But there's your, what the heck, is this like a, it just looked really short. I guess it's compressed. I thought I forgot to know. How many d orbitals are there? Always 5. So how many electrons can they hold? Total? 10. How many elements are in there? 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, wow. So quantum theory was able to explain how the periodic table came about. And then you're back to 4p. So if you will, D trails behind 1. right? You got 4s, and then you go 3d and pull that. And then you're back to 4p. The F trails behind 2. So you come down here to cesium, 6s1, 6s2, and then 4f, you're filling that, and then 5d, and then 6p. So the F trails behind 2. The first F allowed is 4, but you don't start filling it until you get up to 6s. And just follow your periodic table. Follow the atomic numbers. And I hate this periodic table because, is this the one? Yeah, this is the one. It's the one. 1, 2. Yes, I hate this periodic table. This is wrong. The lanthanide and actinide need to go up there in the D, like your book. Why? Because you want to have, here it is here, right? There it is. You can't see it. I've got the ink over it. There's lanthanide right there and actinide. They're up there. That's the way you want to do it, because that gives you now 14 elements down here, which is what you want, because there's 7 d orbitals, right? And that's what your book has. It's got lanthanide and actinide in your front cover up top. That's where you want them. These tables are terrible. I don't know who picked them out. Questions? I'm curious where I'm at slide-wise. 54, that's not bad at all. Okay, we're gonna end with this then. Electron configurations of alkali metals. Condensed would be helium 2s1 for lithium. Sodium would be neon 3s1, and argon, potassium would be argon 4s1. All elements in the alkali metal family have the same ns1 valence shell configuration. This is what we've been saying all along. They behave similarly. They form similar compounds, things like this. They have the same electron configuration. So it makes sense that they all form +1 cations, right? They lose that 1 electron, and now they have a full shell. You see? They're right here on the periodic table. These guys right here. If they lose an electron, then they have the same electron configuration as the noble gas does previous to it. Still lithium, because its atomic number is still lithium's atomic number. It's just the lithium ion, the sodium ion, and the potassium ion. And they have this configuration that's comparable. We say it's isoelectronic. So if you will, lithium, I don't need that, I just need to stay here. Lithium is isoelectronic, if you will. The lithium ion, not the element. So draw a line here. The lithium ion is isoelectronic with helium. That means it has the same electron configuration, which is just 1s2 for helium. And sodium is isoelectronic with neon. Sodium has how many electrons? And if it loses 1, it therefore it has 10. And neon has how many electrons? 10, so they have the same electron configuration. So it's going to be isoelectronic with whatever your condensed form or previous gas, noble gas is. How I've got locked out of my presentation again. So we're done.